Nobody is driving this robot. There's no joystick, no pre-programmed route, and no map loaded beforehand. When it starts, the robot basically knows nothing about the room, but as it moves around, it builds a map of its surroundings and decides where it should explore next. This is called autonomous exploration, and in this video, I'm going to show you how I built it using a Raspberry Pi 5, ROS2, LiDAR, and nav2. And most importantly, I'm going to show you what actually went wrong along the way, because getting a robot to work is usually a lot messier than the final demo makes it look. Before we look at the robot, let's talk about ROS2. If you've never used ROS before, the name can be kind of confusing. ROS stands for Robot Operating System, but ROS2 isn't actually an operating system. Linux is the operating system running on the Raspberry Pi, and ROS2 is more like a communication framework, and it gives all the different programs on a robot a way to communicate with each other. So think about everything a robot needs to do. One program needs to read the LiDAR, another needs to build a map, another needs to figure out where the robot is, another needs to plan a path, and another needs to control the motors. So instead of putting all of that into one giant program, ROS2 lets us split it into smaller programs called nodes. So a node is basically a program that has one main job. For example, we can have one node for the LiDAR, one for the motors, one for mapping, and one for navigation. These nodes communicate with each other using three main systems: topics, services, and actions. Topic is like a constantly updating information channel. Imagine a weather station constantly announcing the temperature. Any program that wants the temperature can listen to that channel. In ROS2, the LiDAR can publish measurements to a topic, and another node can subscribe to the topic and use the measurements. The important thing is that the LiDAR doesn't need to know who's listening. It simply publishes the data. A service is different. It's more like asking someone a question and waiting for an answer. You send a request and then you get a response. So services are useful for quick operations that don't take a long time. And then finally, we have actions, and actions are useful when something takes time. For example, telling the robot to drive somewhere isn't instant, and the robot needs to move, give us feedback about its progress, and eventually tell us whether it succeeded. We might also want to cancel the movement halfway through, and that's exactly what ROS2 actions are designed for. Now let's look at the actual robot. I'm using a High Wonder Mentor Pi. First, the Raspberry Pi 5. This is basically the brain of the robot. It runs the ROS2 software and makes the decisions. I'm running ROS2 Humble inside a Docker container. And Docker basically lets me package the software environment into one isolated setup, so I'm not constantly fighting with different Python packages and system dependencies. Next is the LD19 LiDAR. LiDAR is one of the most important sensors on this robot. It spins around and measures how far away objects are. So instead of seeing a normal camera image, the robot gets measurements like there's something 2 meters away, 50 centimeters away, or there's nothing in this direction. By doing this over and over as the robot moves, we can build a picture of the room. Next, there's also a depth camera mounted on the front. I'm not going to focus on that today because it's not central to this program. Finally, there's the High Wonder controller board. This sits between the Raspberry Pi and the physical hardware. It controls the motors, reads the wheel encoders, and provides information about how the robot is moving. So what exactly do we want this robot to do? We want to put it somewhere in a room with no map and have it figure out where it is, build a map, avoid obstacles, decide where to explore next, eventually recognize that it's finished, and save the map. The easiest way to build this is to split those responsibilities between three different systems. First, we need SLAM. SLAM stands for Simultaneous Localization and Mapping. That's a complicated name for two things. Localization means figuring out where the robot is. Mapping means figuring out what the environment looks like. We're using a package called SLAM Toolbox for this. Once we have a map, we need the robot to actually move through it. That's where nav2 comes in. nav2 is the navigation system for ROS2. We can give it a destination and it figures out how to get there while avoiding obstacles. But there's one problem. nav2 can drive to the destination, but it doesn't decide what destination we should choose. That's the part I wrote. I created a package called Explore with a node called Frontier Explorer. Its job is to look at the map, find areas where the robot hasn't explored yet, and choose the next place to go. Finally, we need a launch file. The launch file starts all of these systems and makes sure they can communicate with each other. Okay, so here I am in the Docker container from MentorPy, and here's where I have my launch file and packages. So it's going to take a bit to start actually running. So the robot is currently in my living room, and it takes like 30 seconds for command velocity to start publishing, since I added a delay in the code. Okay, so now that I hear the robot moving, I'm going to go on my PC's terminal and start up ROS2. So here we see ROS. So here is ROS2 showing the map being created. So let's start with SLAM Toolbox. Its main job is to take the LiDAR data and the robot's movement information and use them to build a map. The map is represented as something called an occupancy grid. So it's basically a giant grid of squares. Each square has a value that tells us what the robot knows about that location. Unknown. -1 means unknown, and the robot hasn't observed that area yet. 0 means free, and the LiDAR has seen that area and determined that the robot can move through it. Occupied means there's something there, like a wall or another obstacle. So gray is unknown, white is free, and black is occupied. And these three states are extremely important because the exploration algorithm I'm using depends on knowing the difference between somewhere that's empty and somewhere we simply haven't looked yet. Next is nav2. nav2 can look complicated because it's actually made up of several different nodes, but we can understand them by thinking about what happens when you tell the robot to go over there. First, we have BT Navigator. This is basically the supervisor. It coordinates the navigation process and decides what should happen if something goes wrong. Next is the planner. The planner looks at the map and figures out a path from the robot's current location to the destination. You can think of it like Google Maps for the robot. It searches through the map for a route that avoids obstacles. Then we have the controller. The planner gives us a path, but a path on a map isn't enough to control the motors. The controller turns that path into actual movement commands. Then there's the behavior server. This handles recovery actions. If the robot gets stuck, it might try spinning around, backing up, or waiting before trying again. Finally, there's the velocity smoother. It makes sure the robot doesn't suddenly jump from one velocity to another. Basically, it smooths out the motor commands. nav2 also uses something called cost maps. A cost map is basically a map where different areas have different costs. High-cost areas are places the robot should avoid. Low-cost areas are safer to travel through. There are two main cost maps. Global cost map. The global cost map covers the larger environment. The global planner uses it to figure out the overall route. The local cost map is much smaller. It focuses on the area immediately around the robot. This lets the robot react to obstacles that might not have been in the original map. The cost maps are also built from different layers. One layer contains the existing map, another adds live LiDAR obstacles, and another layer adds a safety margin around obstacles. The safety margin is called inflation. It makes sure the robot doesn't plan a path that's technically possible for its center point, but too close for the actual body of the robot. Now we get to the part that I actually wrote, the Frontier Explorer. At this point, we already have two important pieces working. SLAM is building the map, and nav2 knows how to drive the robot to a destination. But there's one problem. nav2 can answer the question, how do I get there? It doesn't answer, where should I go? That's what Frontier Explorer does. The basic idea is actually pretty simple. The map is just a grid of cells. Each cell is either free, occupied, or unknown. Free means the robot knows it can drive there, occupied means there's an obstacle, and unknown means the robot hasn't seen that area yet. So I look for the boundary between the free space and the unknown space, and that's called a frontier. A frontier is simply a free cell that's next to an unknown cell, and that's useful because it's a place the robot can reach where it can potentially see something new. So the basic strategy is go to the edge of what you know, then look at the map again, then go to the new edge of what you know, and keep repeating that until there are no useful frontiers left. First, the explorer listens to the map coming from SLAM Toolbox. Every time a new map arrives, I save the newest version. Then, whenever the exploration loop runs, I can ask, what's the latest map? Next, I need to know where the robot currently is. We get that from TF, which is a core library that lets a robot track multiple coordinate frames over time. TF stands for transform. This tells me the robot's position on the map. Now I have two pieces of information. What does the room look like and where am I? Now we can actually look for frontiers. I go through the map and separate the cells into 3 groups: free, occupied, and unknown. Then, for every free cell, I check its 4 neighbors: the cell above, below, left, and right. If one of those neighbors is unknown, I mark that free cell as a frontier. But now we have a problem. A single wall might create dozens of neighboring frontier cells. We don't want the robot to think those are 30 different destinations, so I group connected frontier cells together. So now the robot sees this wall as one frontier cluster instead of dozens of separate points. And we also throw away very small clusters because they're usually not useful enough to explore. For each cluster, I choose a point near its center. Then, I check the area around that point. If there's an obstacle too close to it, I throw that candidate away. I also check my blacklist. If the robot has already tried to go to that location and failed, we don't want to send it there again. At this point, we may have several good frontiers, so we calculate the distance from the robot to each one. Then, sort them by distance, and the closest valid frontier becomes the next goal. This is a simple strategy, but it works well for a small indoor environment. Instead of making the robot drive all the way across the house, we generally explore the closest unknown area first. At this point, the Frontier Explorer has made its decision. It knows exactly where it wants the robot to go. We turn that point into a ROS2 goal and send it to nav2. And this is where I hand control over to nav2. My Explorer doesn't need to worry about individual wheel speeds or avoiding every obstacle. nav2 handles all of that. This node simply says, go here. While the robot is moving, the Explorer waits for nav2 to finish. We also set a timeout so the robot doesn't stay stuck trying to reach the same goal forever. If nav2 succeeds, great, the robot has reached the frontier. If it fails, we add that location to the blacklist and choose another frontier. Now we repeat the entire process. The robot has reached the frontier, so its LiDAR can now see more of the environment. SLAM adds that new information to the map. The Explorer gets the updated map. It finds new frontiers, it chooses the closest valid one, nav2 drives there, and the cycle starts again. Eventually, there aren't any useful frontiers left. The Explorer checks a few times to make sure the map really isn't changing anymore. If there are still no valid frontiers, it declares the exploration complete and saves the map. So that's the entire idea behind the algorithm. It's not following a pre-programmed route. It's repeatedly looking at what it knows, finding the edge of what it doesn't know, and choosing somewhere to go next. And that relatively simple loop is what turns the robot from a remote-controlled vehicle into an autonomous explorer. Now here's some of the problems that I ran into. First, the cost maps were listening to the wrong topic. This one was particularly dangerous. The robot would plan a path straight through a wall. And the reason was simple. The LiDAR was publishing its data on scan raw, but the cost maps were listening to scan. Those are two different topics. So nav2 wasn't actually receiving the live LiDAR data. From nav2's perspective, there were no new obstacles. So what I learned from this is that if a sensor-driven system behaves like it can't see a sensor, check the topic name first. Another problem I ran into were 2 nodes that were trying to control the robot at the same time. And this problem caused some really weird behaviors. The robot would twitch, stop, spin around, or ignore the path. And the problem was that 2 different nodes were publishing movement commands to command velocity. nav2 was sending commands, but the High Wonder joystick node was also sending commands. So basically, we had 2 nodes trying to control the robot at the same time.
and the fix was to stop the joystick control node when running autonomous navigation. So what I learned from this is to always check how many nodes are publishing to your robot's movement command topic. The third problem I ran into was I also found some nodes appearing twice in ROS2 node list. Some were leftover processes from an earlier run, but one of those nodes had another problem. It was configured with respawn equals true. That means if this process died, start it again. So when I would kill the process, the launch system would immediately start it up again. So I learned that if a process keeps coming back after you kill it, we have to check the launch file. Last but not least, one of the biggest issues I had was every time I rebooted the Raspberry Pi. The Pi doesn't have an RTC battery, and when it's running without internet access, it can't automatically synchronize its clock. That means the system can start with the wrong time. And that sounds harmless, but ROS2 uses timestamps everywhere. If messages have incorrect timestamps, systems like Transform can reject them because they appear to be from the wrong time. And there was also another reboot problem. The LiDAR device names weren't always being assigned the way I expected. And I fixed that using Linux UDEV rules, which let me create predictable device names for the hardware. So the lesson was, on an embedded robot, the operating system and hardware setup are part of the robot too. So to combat this issue right now, I sync the time manually from my host to my Pi. So what are some key things I would take away from this project? One is to split the system into 3 separate jobs. First, SLAM builds the map, Nav2 handles navigation, and my Explorer chooses where to go. Because they're separate, we can change one without rewriting everything else. 2 is use actions for long-running tasks. So actions are useful when something takes time. Driving somewhere is a perfect example. You want progress updates, you want to know whether it succeeded, and you want to be able to cancel it. 3. Don't rely too heavily on timers. So the startup timing matters. Using a 5-second or 15-second delay is easy, but it's not very reliable. A better system checks whether the thing it needs is actually ready, and that's something I would like to improve on for this program. And then 4, which was one of the most important takeaways, was to learn the ROS2 debugging tools. So learn how to inspect what's happening inside ROS2. Commands like ROS2 node list, ROS2 topic list, ROS2 topic info, and etc. And these are all incredibly useful. When you're working with robotics, knowing how to see what's happening inside the system is just as important as knowing how to write the code. And that's the basic architecture behind this robot. The LiDAR gives the robot information about its surroundings, SLAM turns that information into a map and helps the robot understand where it is, Nav2 figures out how to move safely, and my Frontier Explorer decides where the robot should explore next. The important part is that all 3 of these pieces work together in a feedback loop. What really helped me with this was understanding the 3 separate ideas, and then once I understood that architecture, all of the individual ROS2 concepts started fitting together. I hope you could find this video useful, and thank you for watching.